So this is a new chapter, boundary value problems, Laplace and Poisson equation. So till now we have been doing problems where you are given charge distribution and you have to find electric field and magnetic field. Sorry, electric field. You have to find electric field and potential. You are given a charge distribution and you have to find electric field and potential. Here you won't be given the complete description of charge. You will be given either no description of charge or some partial description of charge, and you will be given some boundary conditions, right? You will be given, you won't be knowing completely what the charge distribution is. You will be given some boundary condition, and from those boundary condition you have to generate how the field and potential is varying, right? For that, these two equations are very important. They are not very different. See, from Gauss law, we know from Gauss law you have flux of electric field E dot NDS equals to Q by epsilon naught. So this Q, we can use Gauss divergence theorem. So Q can be written as rho d tau. All this can be written as del dot E equal to 0. Since this integral is 0 for volume enclosed by any arbitrary closed surface, this integrand has to be 0. That is minus, or we can write del dot E equals to rho by epsilon naught. Del dot E equals to rho by epsilon naught. Alright. This is the differential form of Gauss law. This is the differential form of, you can say, Gauss law. Now, if I put, since E is conservative field, it can be written in terms of gradient of a scalar. So this becomes rho by epsilon naught. So this becomes minus of, all this is del square V, that is called, we call it Poisson equation, and F in the medium rho is 0. So you have, for the medium where you don't have the charges, this is called we call it Laplace equation. Call it Laplace equation. This is Laplace equation. So we will be using these two. If the region of is a region under consideration where you have to find electric field and potential, if there are charges, we will be using Poisson equation. Where there is no charge, I will be using Laplace equation. So I will be taking a problem in order to explain this. Let me consider a problem. See, the plates of parallel plate capacitor, which are normal to x-axis, are located at x equal to 0 and x equal to L. The plate at x equal to 0 is grounded while other plate is at potential V. The space between two plates is chargeless. Find the Laplace equation which is valid between two plates and integrate this equation to obtain the potential Vx and the electric field between the two plates. See, we have to solve this. Alright, let me draw these plates. The other two plates, this is at x equal to 0, this is at x equal to L, and between the two plates the region is vacuum, right? So the potential at this plate is 0, this is grounded, and here the potential is V. Let's call it V naught. So the potential distribution can be V is 0 at x equal to 0 at x equal to L. Now in the region between the two plates there is no charge, so I can apply the Laplace equation del square V equal to 0, which is del square V is this, zero. Now you see that, V is 0 at x equal to 0 and V is V naught at x equal to L. Means on this whole plate, this infinite plate in YZ plane, at every point of this plate your V is 0. See, any general point of this plate can be written as 0 YZ. Means on this plate Y and Z coordinates are varying. Y and Z coordinates are independent variable. They are unrestricted. They are unrestricted. But V is remaining 0. What does it mean? It means V may not be varying with Y and Z. Now on this plate any general coordinate can be written as LYZ. So now V is V naught. At x equal to 0 V is V naught, V equal to 0, and at x equal to L V is V naught, and V is not varying on this plate. Means all the points on this plate is having x coordinate L and Y and Z is varying on this plate, but at every point V is V naught. What does it conveys? It conveys it gives you an idea that V is varying with x, because when x changes from 0 to L V is changing, but when Y and Z is varying on these individual plates V is not varying. It means V is function of x only. It is independent of Y and Z. So this is going to be 0. This is going to be 0. Since V is a function of x only, it can be written like this. If I integrate it once, I'll get d by dx equal to c1, or if I integrate it once more, I'll get c1x plus c2. Now at x equal to 0 V is 0, so c is 0. At x equal to L V is V naught, so we can write c1 equals to V naught by L, or the potential distribution can be written as, I can write the potential distribution as V by x. This Vx is V naught by L into x, and the electric field, which is minus del V, can be written as V naught by L I, right? You can write like this, V naught by L I, actually minus V naught by L, sorry, minus V naught by L. Alright, so this is how we can find electric field and potential.